on the ground shines on a wall 12 meters away. So we have a spotlight on the ground. Here's my light. Light's coming out. Oh, it's a spotlight, sorry. It's spotlight. There's my light. Looks like a cannon. Okay, here's my wall 12 meters away. That should stay fixed the whole time. The light's shining onto this. It's supposed to be a straight wall. All right. If a man 2 meters tall walks from the spotlight toward the building, so there's a man who is 2 meters tall. He's walking towards the wall of the building, right? And he's moving at a speed of 1.6 meters per second. How fast is the length of his shadow on the building decreasing when he's 4 meters from the building? So you imagine his shadow is on this wall. Right now, the shadow is being cast up like this. So you've got, here's his shadow on the wall, but as he gets closer to the wall, this line comes down, so his shadow starts to shrink. So we want to know how fast his shadow is shrinking. So here's my general picture. I'm going to draw this. Here's the spotlight. Here's the wall, straight up. This is 12. That's never changing. This point I don't need yet. I'll just say that. And then I have the man in here, which I'll represent with this line segment. That has a measurement of 2 meters. And then I have the shadow. The tip of the shadow is coming up like this. That casts to a point right there. I know that he is moving this direction at 1.6 meters per second. So I have a couple of ways of doing this. I can say, like, this distance from here to here is x, and then I have dx dt is 1.6 meters. Then I can call, hold on, sorry, 12 meters was this. Jeez, Robert, 12 meters. This right here goes from here down to here. This is, let's call it y, and that's shrinking, and that's what I want to know, how fast y is changing. So that's one way I could set it up. Another way I could set it up is, which would also give you the same answer. There's your 2 meter man, there's your 12 this way, is to call this from here to here x, and then from here to here we call that y. And then the way the problem is worded, if he moves this way at 1.6 meters per second, then dx dt, the rate at which x is changing, is shrinking, so that would be negative 1.6 meters. Either way. So it's really kind of your call here, how you want to do this. So we'll flip a coin. This one, okay. We're going to do that, so forget this one. That's my general picture. At the instant in time, I think I'm going to regret doing it that way. He's 2, this is 12, and he is how far from the wall? Let's see. We want to know when he's 4 meters from the building. 4 meters would mean that this is 4, right? And if the whole thing is 12, then that would mean that this would have to be 8. So that means x is 8 meters at the instant in time, because it corresponds to that. And then y here, we should be able to find. We should. Let's write down what we're given and what we want. So I am given that x is changing with respect to time at a rate of 1.6 meters per second. I want to know how fast y is changing with respect to time at exactly the moment that x is 8 meters. So now I just need an equation that relates x and y together, and that means I need to try and work with some similar triangles again. All right, so let me draw my two triangles, this one right here. I'm going to go off this general picture. So I have a small triangle, x and 2. This is a right triangle. It has an angle like that. And we'll label that angle like that. And the distance from here to here, the big one, the big triangle, this is y, this is 12. This angle is the same as that one. This right angle, this angle is the same as that one. So they're similar triangles. So I can set up a ratio however I want. Let me go this one. I'll just go 2 over x equals y over 12. And that's the equation that relates x and y together. So now I can take the derivative of that implicitly. I think I'll do that right here. So here's my equation. So just remember that this right here is 2 over x is the same as 2x to the negative 1, because I'm going to do derivative. And then over here, remember, y over 12 is the same as 1/12 y. So let's take derivative on this side. We have to do some power rule. Negative 1 comes out. So negative 2x to the negative 2, very important there. Then the derivative of what was there, so dx dt, equals, now 1/12 comes for the ride, and then times the derivative of y with respect to time, which is dy dt. And I kind of got in my own way here. But notice that in order to answer this question, I need to know what? I need to know what x is, I need to know what dx dt is, I know those, and that'll help me solve for dy dt. So let me rewrite the equation. This is negative 2 over x squared times dx dt must equal 1/12 times dy dt. And so now let's plug everything in. I know that x is 8, so this is going to become negative 2 over 8 squared, which is 64, times dx dt, which is 1.6. That equals 1/12 times 6y, dy dt. So I think I'll need to get my calculator out for this. Well, that actually will be a nice number, but yeah. This left side, the whole thing, becomes negative 0.05 equals 1/12 dy dt. Then multiply both sides by 12. 0.6, negative 0.6. So we get dy dt is negative 0.6, and then y was measured in meters. Time t was measured in seconds, so this will be meters per second. So it's shrinking at a rate of negative 0.6 meters per second when he is 4 meters from the wall. This was number 6. Yep. All right, 16, sorry. Number 24, is this the last one? Man, there's a lot more problems in here that we could do. Finally, some geometric one here. 24. Water is leaking out of an inverted conical tank at a rate of 10,000 cubic centimeters a minute. Oops, sorry. I'm going to be doing number 24. I had a little technical issue there. 24, interesting problem. You have conical cup or tank. It's 4 meters diameter, 6 meter height. You've got water in here. There's a leak and water is pouring out. At the same time, water is coming in. This is coming out at a rate of 10,000 cubic centimeters per minute. The rate that it's going in, all you know is that it's going in at a constant rate. And they tell you that when the height is 2 meters, the change in height with respect to time is 20 centimeters per minute. Let me just double check all that. All right, that's basically what you're given, and they want to know how the rate at which it's going in here. So a couple of things, I need to draw some pictures and label some stuff. So my general picture is this water in here. This water has some height to it. We know that this is always 6. We know that this is always 4. But there's a key point right here in the problem. We need to remember everything that we have here, the rates are in centimeters per minute, and this is measured in meters, and this is meters and meters. So I want to convert from meters to centimeters. So let's convert this. This is going to become 200 centimeters. This will become 600 centimeters. And this will be 400 centimeters. So we're just converting over. That way all of our units are the same. Let me just make sure I'm doing my work right here. It was 6, right? Yeah, okay. So that's our general picture. The instant in time, they tell us that we've got water that is 200 centimeters. So down here, okay, and they tell us that this is, H is 200 centimeters. And of course, we know that this is still 600 centimeters and 400 centimeters. So what we want to know, right? We want to know the change in volume with respect to time, which is going to be how much, well, we want to know how fast water is going in. Let's think about the total change in volume. If you have water going out and water going in, then the total net change in volume with respect to time should be the negative 10,000, that's the going out, plus some constant, which is the water coming in, right here. So maybe that's 20,000 cubic centimeters a minute. But if you take 20,000 and you subtract 10,000, then the net would be 10,000. Or if that was 30,000, 10,000, then the net would be 20,000. So we know this to begin with, all right? dV dt is going to be how much is going out plus how much is going in. We want this, okay? We want that, and we're given that at H is 200 centimeters, that dH dt, the change in height with respect to time, is 20 centimeters per minute, which means that as we do this, as this happens, the water level is actually coming up. At exactly the moment that the height is 200 centimeters, the water level is actually rising. All right, well, let me see if I can't come up with an equation that's going to relate H and V together. Well, I'm looking for the volume of the water, and the volume of a cylinder, a cone, is 1/3 pi r squared h, which this formula would be good because it has h in it, it has v in it, but it also has r in it, and I don't have an r in the problem. So this is like what I did in class. I'm going to have to slice this general picture down the middle, and if I slice this cone down the middle, I'm going to get a triangle within a triangle. There's actually two sides to it like this. There's our cone, here's our water level, but we're just going to look at half of it. So that's all that matters. We have a little right triangle here and a right triangle here. This right here is 600. This right here is half of 400. Remember, it was 400, so this is 200. This little piece right here is the radius of the water, and this right here is the height of the water from here to here. So I get my little triangles there set up. I can write them out like this. This is 200, 600. The smaller triangle. I'm going faster just because we do something like this in class. There's my similar triangles. And so I set up a ratio. I'm going to go h over 600 is r over 200. h over 600 equal to r over 200. I'm going to solve this thing for R, so I can replace that R. So I'm going to multiply both sides by 200. I'll get 1/3 H is R. And I'm going to replace that and put it right here. So volume will be 1/3 pi times 1/3 H squared times H. So now square that. That's going to be 1/9. Multiply it out here. Volume is 1/27 pi. I have H squared times H again. That's H cubed. And there's my equation that has V and H in it. I differentiate with respect to time. dV dt equals constant times constant. There's H cubed. Take derivative. 3 pops out. 3 times 1/27 is 1/9 pi H squared times chain rule dH dt. And I know dH dt is 20. I know at the moment that H is 200. So dV dt should be 1/9 pi times H, which is 200, squared times dH dt, which is 20. And let me break out the calculator. And I'm going to multiply that all out and see what I get. So, whoa, that doesn't seem right. Yeah, I guess so. Okay. Let me go back to it. I accidentally deleted it. Whoa, that's a big number. Just double check. This didn't seem right there. Times 20 times pi divided by 9. Yeah. So this is dV dt is 279,252.68 approximately. 279,252.68. Volume here is measured in cubic units. My units were centimeters, so centimeters cubed per time unit is minutes. But we're not looking for dV dt. dV dt is the negative 10,000 plus the C. We want to know what C was. So what I'm going to do now is I'm going to just write that equation. 279,252, I'm just going to round it right there, is equal to negative 10,000 plus C. Let's see what C was. So add 10,000 on both sides. You should get 289,252 cubic centimeters per minute is equal to C. So I just added 10,000 on both sides. So basically what's happening is this. You got 289,252 cubic centimeters per minute going in. You've got the 10,000 going out. And when that happens, you'll have the correct, the height will come up at 20 centimeters per minute at exactly the moment that it's 200 centimeters high. Whew. The main thing was how fast are we pumping the water in, and that's it right there. I know that's a confusing problem, and that's why it's the last one. I will say, though, there are many other problems here which are good problems for you to look at. Ones that I just breezing through here. Number 17 is good. Number 20 I like. So 17, 20 are good. $27 is good. $28. Those are all good problems. Those would be fair problems on the test. I just don't want you to think that the problems you'll see on the test are exactly like these. All right, good luck with those. Hope it goes all right.